Hello, everyone. My name is Dennis Bernardes, and I'm from National Institute of Espaciais Research, Brazil. Well, I want to thank you guys for the good opportunity to present my work, and I hope you enjoyed this presentation. I will talk about the Spark 4 simultaneous polarimeter and rapid camera in 4 bands, an acquisition, and an overview of the instrument acquisition system. Brief summary of what I want to talk. We'll present the Spark 4 itself, then the acquisition control system, or the ACES, developed to control the Spark 4 cameras, then some first results using this ACES, and finally, how the polarimetric mode works and some synchronization solutions. Here you guys can see a picture of the overview of the mechanical structure of the instrument. It's quite similar to the was presented for the dipole, and it was a nice presentation. So here you have, following the light path, we have the auto-guided system responsible for the guidance of the telescope during the night. Then we have the polarimetric module with the retarders and analyzer for polarimetric acquisition. And then we have the camera set composed by 4 cameras, 1, 2, 3, and 4, and right behind. The Spark 4 will be installed on the 1.6 meter telescope at the Pico dos Dias Observatory. He is the site where the observatory is, and right here is the building where the Spark 4 will be installed. Spark 4 will allow photometric and polarimetric acquisitions in 4 of the 5 bands of the SDSS system that are G, R, I, and Z bands. Also, we use 4 EMCCDs with 1000 by 1000 pixels, and we have a field of view of 5.6 by 5.6 square icon minutes. And this instrument is being developed to the study of variable phenomena like exoplanets and exoplanet transits in remote observations. Okay, moving forward, here we have an explosive vision of the polarimetric model of the Spark 4. This system was based on the polarimetric technique developed to the IGPO. That's another instrument already used at the observatory. This guy right here is the calibration wheel with all the components for the calibration of the polarimetric. Here we have the wave plate with half and quarter wave plates for linear and circular polarizations. Then right here we have the analyzer that is a subpart freeze. So we were able to occur the ordinary and the extraordinary rays at the same time. And this system or this polarimetric optics can be out of the beam, allowing us to do some photometric acquisitions. Moving forward, here we have the camera set. Right here, there is the collimator, and inside this box we have 3 dichroic mirror responsible for separating incoming light in the 4 spectral bands. With each one of these output, we have 1 Axon Ultra 888 EMCCD cameras produced by another technology company. They are frame transfer devices with the electron multiply capability. And also, they have a coding and window optimized for the respective spectral band where each one of these cameras will operate. Moving forward, here we have the current state of the instrument. Right here, you guys can see the polarimetric module. And in this right figure, you can see again the overview of the mechanical structure, but this is the real one. And now I want to talk about the acquisition control system, again, the ACES, that is the focus of my work, my PhD work. The ACES was developed to control the Spark 4 cameras, like this guy right here. And we use the LabVIEW programming language with the SDK package provided by the Android technology to communicate with these cameras. And the ACS allows simultaneous and synchronized acquisitions. And to meet that, it uses a digital pulse generator, or DPG, with a resolution of 10 picoseconds. This is the figure of the pulse generator. And how we do that? We prepare each one of these cameras to receive an external trigger. And when we do that, the pulse generator sends a synchronized interforce, synchronized pulse for each one for these cameras, and this synchronization will be with a 10 picoseconds on resolution. If you guys have a little more interest, you're on GitHub, you can look for the Bernardes/Spark forums for ACS. And this is a small graphical engineering interface that I developed to control the ACS. This is not the final version of the user interface, but is quite similar to it. And using this engineering interface, we were able to do some simple tasks like accurate image cubes. And an image cube, I mean a unique file with several frames accurate continuously. And we can also use the control the cameras by command line and control the operational mode of the CCD cameras, or also write some important information in the image header. Okay, now I will present some first results that we obtained using this software. Here you guys can see a graph of the time as a function of the cube size of the cube in frames of the main steps needed since we acquire one image by the cameras until this image being saved in the hard disk of the computer. And these steps are write the data in the feeds file, write the standard header, write the delays of this frame also in this header, transfer the data from the cameras to the lab view, open and close feeds file. All this process need a considerable amount of time, and we manage all this process to optimize the performance of the ACS. And when I say optimize the performance of the ACS, I mean obtain the smallest dead time between the acquisition of two image cubes. So some results with using the ACS and the obtained dead time. Here you guys can see a table with the size of the cube in frame as a function of the dead time between two cubes, and our best result was a dead time of below 1 second between acquisition of two image cubes with 107 frames of 1000 by 1000 pixels. A second result was a dead time of 4.6 seconds between two cubes with 1000 frames and 200 by 200 pixels. As a reference, at North Germany, where there is the Allopec instrument, they were able to obtain a dead time of 4 seconds as a comparison with our result. Okay, now I will present how the polarimetric mode actually works and some synchronization solutions we found for the system. Okay, first of all, we need to position the wave plate at the right angle to the image. Then we need that the digital pulse generator signals to the CCDs to start a new acquisition. And at the end of the exposure, we need that the wave plate moves through the next position, and the cycle repeats over and over and over. Okay, but we need some kind of communication between each one of these steps to the system works. And we're planning to do this using hardware communication to minimize the dead time between each one of these steps. And for the wave plate, the model of the wave plate will signal to the pulse generator when the wave plate is in position. And when the receiving this pulse, the pulse generator signals to the CCD start a new exposure. but we still need to find some kind of signal produced by these cameras to warn the wavelet to move to the next position. And here I present our solution for this problem. And this is the graph of some I/O signals provided by the MCCD cameras measured by using an oscilloscope of the signal in volts as a function of time. In black, we have
5 minutes.
Okay.
Sorry, 5 minutes.
In black, we have the external trigger pulse as a reference. So each one of this block is an image cube, and this image cube has 5 frames, like you can see by the fire signal 1, 2, 3, 4, and 5. And in red, we have the fire, in green, we have the arm, and in blue, we have the shorter signals. In advance, we discarded the shorter signal because we don't need that shorter switching between positions. So in between these two signals, the fire is the best solution because at the end of the exposure, we have this transition from the high level to the low level of the camera. So this is the most suitable signal to move the wave plate. And also, we can use the arm signal as a feedback to the pulse generator, warming to it when the camera is ready for the next acquisition. Okay, this is my last considerations, my conclusions, and I want to thank you for the opportunity.